for this opportunity and to give time Carlos to come in and take his seat. That's my first time in Brazil and in South America, unless Mexico counts. It doesn't count? Okay. Yeah. So I changed a little bit also the title because originally I was planning to talk only the first type about the cosmological implications, but then I decided that I can show you a little bit of current paper that we've submitted for peer review. So this is a research that I've been doing with Professor André Mader from the Geneva Observatory. He retired about 10, 12 years ago, but he's as active as I never seen any researcher being so active, and active in a variety of fields, and basically it's his nature. So basically the scalar variant vacuum theory, that's his idea that I will try to explain to you and hopefully to convince you that there is a lot of rational in this idea. So short outline of the talk. Of course, it's always good to start with brief motivation about a specific model or idea, but since we don't have time, then this would go back for the discussions. So what I will do, I will talk about briefly about the mathematical tools of the scalar variant theory and basically how one can arrive at the equations for gravity and cosmology within the theory. Then I'll present the growth of the density perturbations. That was a paper that was published in Physics of the Dark Universe earlier this year, and it was also in the archive on the first slide. Later you can see also the reference to the original journal paper. Then my plan is to talk a little bit more about other viable applications of the theory. I was particularly involved with the growth of the density perturbations, and I'm involved with the dwarf spheroidal. That's the second part of my talk. Now, there are two other applications there, the Hubble expansion and magnitude H data, also the CMB and nucleosynthesis. They are papers that Professor Mader have put in the archive or have published, and I'm ready to discuss his results. But the thing is that these are basically discussing his papers, and I haven't been able yet to having time to go through his calculations and confirm them. Unlike the other first, the density perturbations, I verified his calculations, and also with the dwarf spheroidals, I'm confident and I understand what is going on there. So that's why the other two topics also we can discuss it later. And then I'll conclude the end of my talk with the conclusions and any questions. So with this in mind, I would like to point out that symmetry is very important in physics. We don't understand really why the symmetries are the way they are and how they arise, but definitely they help us a lot in solving physics problems. Example is Newtonian physics, where you have Galilean invariance. Then once you unify space and time, you arrive at special relativity, and you need Lorentz invariance. Now, of course, the big genius of Einstein was not only did the special relativity, he did the general relativity, which basically said, well, let's allow any observer that is reasonable enough to be described within our framework, and that's how he formulated general relativity and the general covariance. So practically nowadays, all the theories are based on Lagrangians, and the description requires general covariance. Now, there are two other symmetries that are still present in the equations. One in the Maxwell equations, if you don't have charges, just electromagnetic waves, then the equations are scalar invariant. Similar happens with the Einstein equations when you don't have matter. And if your cosmological constant is 0, then again your equations are scalar invariant. But even if you don't have matter, but you have cosmological constant, then you don't have scalar invariance. And that's kind of a problem that seems that Einstein himself didn't like. But today I'll also talk a little bit about Mont. And Mont, basically Milgrom, Mont stands for Modified Newtonian Dynamics. Originally, he modified a little bit Newtonian dynamics, but latest papers, when you look at them, he actually puts a good reasoning saying that, well, the theory should be scalar invariant. And in this case, the scalar invariance means just change the units. You don't need actually to consider local gauge invariance like in wave theory, but just overall global scalar invariance. And then he says, if you have your gravitational theory, and if the gravitational acceleration is strong enough, bigger than some fundamental acceleration, the Mont acceleration, then you'll find that it's actually described by Newtonian gravity. If you go to much weaker gravitational or accelerational motion, less than this constant, then what you see that it's a different behavior for the observed gravity compared to the Newtonian gravity that's in the system. Now, notice that here, this limit is again reaches 0 when Newtonian gravity goes to 0. And basically, these two regimes are described by this type of function between the observed gravitational acceleration and Newtonian or baryonic acceleration.
And I see that the scale factor in the ultraviolet brain.
The A0? Yeah. Yeah. Now, the thing is that this is one of the forms of this kind of behavior. There are other expressions, but I think from what we gathered by looking at Milgrom's papers, that seems to be the favorable kind of form. Now,
this expression that you wrote there, is purely phenomenological.
Yeah, yeah. And we'll compare with this one. I mean, there are other phenomenological kind of people say, well, let's see, there's a general function, and they study all this kind of, so that there's a whole industry of how to deform the Newtonian gravity.
And I see there's approximately C times the Hubble constant.
Yes, and later then, the last slide, you'll see something more than C times Hubble constant. Now, the one thing in Mont is that this theory is successful in galactic dynamics, I mean, fitting the data there. Also clusters, basically, but it has trouble when you go to cosmology. So when you go to cosmology, then they change the function. But that's good enough, basically saying, well, that's what we see, and we try to model. And I'm mentioning this because it's also talking about scalar invariance. But most of my talk, what I'll talk about, would be the Veil geometry. Yeah. Yes, I think that they do the galaxy clusters. But if you go further, so the galaxy clusters are kind of intermediate, and I'm not sure how much they modify their functions. I mean, later when you see, I mean, at the end of my talk, you'll see how they can modify their function. They should be able to get everything. Now, one side comment, I wouldn't talk much about it, but there's one big argument against Mont was that it was non-relativistic and non-covariant. Eventually, I think Bekenstein was the one creating a relativistic model that was unique. Took him 10 years to find the formulation. Then 3 guys from Oxford went and fitted all the data. Everything seems to be fitting well, except for one thing in the cosmic microwave background, which kind of brings Mont down. But we'll compare with the Mont, and my point is here is the scalar invariance within the Mont as a justification. So going back again to Einstein, basically this is the usual element in Einstein theory, where you have a metric, and this would determine the distance between 2 points or the length of a vector. And now, important point is in Einstein theory is that if you have a vector and you transport this vector along the geodesics, the length of the vector doesn't change. Now, the thing is that This is important because Veo actually suggests, well, why not let nature allow gauge invariance? Basically, at each point, we will have freedom to choose our units. And from one point to another, we will let things change. And basically, his reasoning was, well, we can go from one point to another. We can have this length scaling factor. And if we're looking at the length of a vector, well, of course, this should be proportional to the length itself, the displacement between the 2 points. And of course, now to make it covariant, we need some kind of a vector there. And usually it's called like a metric connection. So this gauge transformation could lead to this kind of description. That was the original Veo idea. And of course, there are some problems with that. One problem is that if you're observing a process up here and then somehow the information comes to you down here, there could be another part this information could arrive to you too, and a third way to come. In all these ways, having this kind of dependence, that means that what is happening, your understanding of a process that you're observing would depend on the history. What is happening over time? If it was constant, then you know there's no problem with the history. As long as the vector came to me, then I know what was up there when the process was happening, and I can understand this process. So that was Einstein's main objection, that this would mean history-dependent information about the description of processes, and therefore it will be totally impossible to understand nature just because we don't know all the history, what is happening through process. However, people find a way out, and it's called integrable Veo geometry. And these are some of the main people that are developing in this geometry. So the main idea in the Veo geometry, integrable Veo geometry, is now, okay, we have problem, but if we say that the information that comes to us, doesn't matter how it comes, it always would be for some reason synchronized, then we should be okay. That practically means that if you transport the vector along a closed loop and come back, then the total length shouldn't change upon actually transportation along a closed loop. And this saves you because now it means that any way the information comes to you, it's always the same process and consistent. This is practically now, when you go through the previous expression, this results in something like the Faraday tensor and the area of the loop. And here, of course, you have the length of the vector that you are transporting. So for gravity, we would like to have the total change delta L to be 0. That would mean that this should be 0. And that means that basically the vector k mu should satisfy this equation. But this equation is just saying that if k mu is supposed to be a potential of some gradient of some potential that is smooth, then this would be satisfied. And actually, within the Veo integral geometry, this potential could be related to the scale factor. Now, this brings a whole machinery that has to be developed, because now scalar doesn't mean just scalar, because if you do the scaling of your units, then your scalar may actually change also. And if it changed like end power of lambda, the original gauge function, then this would mean that this is a scalar of order n. That means that now you have to define different way of derivative of a scalar, and this adds additional term. Similar for vector and covector, you have extra terms. But even if you say that you would use vectors and covectors and scalars so that they are zero order, and it's unfortunate that they start talking about covariant and this co too much. But power 0, then still this would be 0, but there's an extra term in your connection. This is the Levi-Civita connection, the usual one in general relativity. So again, you have the original expressions, but now there's an extra term that's proportional to the metric and this field kappa. So that means that even if you selected observable, there's n equals 0, and n equals 0 is actually in scalar, because scalar becomes a little bit too scalar in their terminology. still there will be contributions to the equations of motion. Now, following all this, you have all this machinery, you can develop, of course, the Riemann calculus. And people generalized basically the Einstein equation. And what will happen is that here would be something that would be the Einstein tensor from general relativity. They'll have a bunch of other elements that would depend on the field K and its derivatives. And then again, on this side, you will put, because you will not be able to match the Einstein general relativity as a limit. Here, the matter tensor, and then now you have the cosmological constant. But in this formulation, the cosmological constant comes also with the scale factor together. So what happens is now, even if you drop the Einstein tensor and matter, these become actually generally scale invariant because of the functional dependence on lambda everywhere there. Now, the same action could be derived from the action principle, and it was done by Canido et al. In 1977. So it gives nice framework. There are theories that work on that, basically theories like what was called Brand-Dickey theories. I think dilaton theories and other similar theories where you can have fields like this. Actually, the main contribution, I think the great insight for Professor Mader to come up with his theory was to actually consider dropping these two terms and say, okay, now this would describe the vacuum, what is left. And the vacuum has to be scale invariant and Lorentz invariant. If I want to have an isomorphic and homogeneous cosmology, that means that actually most of these terms should drop out because the derivatives of the lambda, of the gauge, should be independent of the spatial derivatives. So it becomes only one dependent on time. And this time is actually a special one. This is the cosmic time. And there is only one component of the vector k that survives. It's k0. I mean, that's after making sure that it's homogeneous and isotropic, consistent with what we observe at large scales. Now, when you look at these equations, then they actually become only two equations. And they could be solved and give you an answer that is 1 over the cosmic time. Now, the proportionality will depend on the choice of a particular units that you'll use or your gauge, so that this would satisfy these equations. In principle, it's actually a square root of 3 over lambda times 1 over t, if you're using cosmic time. So this is the equations that André Mader actually kind of realized make sense for this description, and that means that now you're killing all these terms. And if you do that, then you're left with just simple Einstein theory without cosmological constant or equivalent cosmological constant if you wish to. But these terms disappear because of the solution for the lambda.
So what is lambda again? Scale factor?
Yes, overall scale factor. Let me see if I can go back quickly. That's here. Yeah.
You modified the connection.
Yeah.
Connection.
Yeah.
The metricity condition still works in this theory?
Well, the metricity is now consistent with this kind of differentiation. So you have to do the cotensor kind of calculations.
Do you have conservation of the energy momentum tensor in this formulation?
Now, it's kind of depends how you look at it. If you take care of everything and decouple the vacuum from the rest, then you have the regular thing. But if you look at the total equation, like you'll see in a moment about the growth of the density perturbations, when you look at the equation for the continuity, actually you'll see a term that looks like matter creation or annihilation. So, other questions? So these are the main kind of things, and now that's good. Now we can go back and do cosmology. And if we do cosmology, the equations for cosmology are very similar based on the previous expressions. And then again, this one known from 77. You can see that there's extra terms. Basically, these two, you can say basically 3 terms here and 4 terms here. But if you include the previous equations, then everything simplifies and there's only one extra term. But lambda now disappears because lambda, when I say lambda, cosmological constant disappears because it was part of the equations for determining the scale factor. So now these equations you can consider in different way. I mean, this is another way to express lambda CDM if you want to, by saying, okay, if I look actually, usually in lambda CDM, this term is lambda over 3. If I have specific behavior so that the scale factor and R is the spatial scale, if they move in a way that it just looks like a scale factor, like a cosmological constant, then this will be pretty much the original one. So these are the terms that come around. The good thing is now if you look at this one, there is no dark energy there. But you can say, well, you actually took care of the dark energy by just making a change in redefining your fields. But later you can see that this may be helping us understand better what is happening in the dwarfs and other systems. Now,
sorry, can you map this to a Brans-Dicke theory? Can you map this theory to a Brans-Dicke theory?
Well, you have to look at the Lagrangian, and I think you can map it as long as you just say that the Brans-Dicke field would be independent of the spatial part, which is not anything that I've seen anyone doing it in Brans-Dicke theory.
So the Lagrangian, so if you look at the action, the only modification is that you have this lambda square R term. Is that what you have? I wrote an action.
So there are two actions. So this is this one that gives you this. Yes. Then, of course, you have the matter one that will come in a second.
Right. So this one is just a nominal coupling.
Yeah.
Of the two gravities.
Just pretty much like Brans-Dicke theories.
Yeah. So this is.
But in what I found, it's nobody in Brans-Dicke theory, people working there, dared and think that, well, what if it's not depending on X, Y, and Z? And that was the key thing that Professor Mader made.
So lambda only depends on time.
Yeah. Otherwise, you violate the isotropy and homogeneity. I mean, if you want isotropy and homogeneity, right, you need to actually demand this, at least at the global scale. I mean, probably in a locally, probably you can open this
it's like a homogeneous
box.
Background.
Yeah. So the good thing is that these equations are exactly solvable. And basically, Professor Mader have done it. That's a very nice paper. When I confirmed some of these calculations. But more interestingly, I mean, there's somebody here in Brazil that did exact calculations, and he actually introduced what is the exact solution for k equals 0. And then we matched these solutions. That means that actually you have a very easy way to say what is your scale factor over time, depending on what is your mass content of the theory. And if you compare with LambdaCDM, actually for any choice of omega m, you'll find compatible equivalents, different value, but a curve that would actually trace back to the LambdaCDM quite well. So for example, here, this is the LambdaCDM for 30, the blue line. This is the 30 for the Scalar Variant theory, and the dashed lines here, the black one, this is at 2.27. That's the kind of as close as possible to the LambdaCDM. So this gives kind of the assumption, that the expectation that the Scalar Variant theory can do as well as the LambdaCDM practically everywhere. And so far, what we have done, we tried different places to see whether we'll run into obstacles or difficulties, and we haven't. So we expect that if we have the time to really do the standard way LambdaCDM was run and identifying all the constants, if really works well, then probably we can get everything right.
So in terms of free parameters, how many extra parameters you have in?
The same like LambdaCDM.
So there's no extra free
parameters? Now, from here, you don't see that dark matter may not be needed, but we can show it in the discussions. These are the rotational curves in galaxies. Professor Mader have done calculations where he claims that you don't need it, that dark matter there. Now, still, you can put dark matter in the model, because you can have the same kind of scaling like equation of states omega minus 1/3 or 2/3, like for dark matter kind of animals. But basically, he wants to stay this close to matter without really invoking unless we really see that the data fits is requiring it. Yeah.
So for omega matter equal 0.8, what's driving the acceleration of the universe?
Like 0.8 here?
Yeah, what's driving the acceleration?
So for omega m, this is I think this is related to the lambda. I mean, LambdaCDM would have cosmological constant, right? And this is what you get for the dashed lines are the LambdaCDM.
I don't know, but I mean physically. So how can you describe the expanding, an accelerated expanding universe with omega matter of 0.8? So what's driving the acceleration?
Still the cosmological constant. But the question is whether you have the cosmological constant like LambdaCDM. So if you put lambda equal 1, then you have the cosmological constant here and here. And here this disappears, but then this term would stay here. So in the LambdaCDM, basically, you put lambda to 1, and then you have the cosmological constant here. If you allow the lambda, the scaling factor, to be dependent on time, but satisfying these equations, then this would take away the cosmological constant, but actually it hides the cosmological constant down here in the solution, in the lambda itself. So you can think that this is a different way of looking at it, and how it appears in the equations, whether it would be like this, or it would explicitly see the cosmological constant. And that's why I think that both descriptions should have equal accuracy in describing the data.
Right, so you have mount plus lambda.
No, there's no mount.
Okay, so
This is Scalar Variant vacuum theory. So the mount, it will come in a second. The Scalar Variant theory is saying this is when I allow for scaling like this, well gauge, and make sure that this gauge is actually consistent with this requirement that if I move along a closed loop, I get 0, which means that I should have this equation. I should satisfy this equation. Or basically, the field kappa, the vector field is generated as partial derivative of lambda. But now to have isotropy and homogeneity, because if lambda spatial part is non-zero, then you would observe inhomogeneity and anisotropy that we don't observe. Therefore, we have to actually insist that it has to be 0, and the only term that survives now is only the K0, the time components.
Okay, so let me see if I got it right. So the only two things that you're not matching is the graphical cosmological scale, right? So you're saying that at some point somehow you cannot reproduce the CMB?
No, the mount cannot reproduce CMB properly, the relativistic mount. We haven't tried to do the CMB. But that's, for me, is the main argument. If mount failed there, that's where we should try to see. And if we fail there too, then of course there's no point. Most likely we will reproduce everything else, but we will fail where mount failed. But if we get it there, then actually that makes more sense to keep doing all the other fits and see what we'll get.
And it's something like Baryogenesis oscillations. Can you also reproduce them?
Well, we have the equations, but we haven't looked into that. I mean, like I mentioned, there is the Hubble expansion, the magnitude Hubble relationships. The CMB, there is actually indications that it should be able to reproduce them, and baryon nucleosynthesis should be able to be reproduced correctly. Thing is that we haven't fixed exactly what are the parameters of the model. I mean, we just need to do like all the data fits and see where the different tests gives you what values of the parameters and then see the overlap.
Okay, so could you show the comparison that you have with the dashed lines, that plot that you showed?
Which one? This one, the cosmology?
Yeah, the cosmology.
Yeah.
what is the red line here? So, exactly
So the red line is the Scalar Variant vacuum theory.
yeah, but what about matter? What do you put for matter?
Oh, so in the Scalar Variant theory, there is only one. I mean, how much matter is there? And the rest is cosmological constant, or dark matter if you want. But the cosmological constant does not enter through the equations here. It enters through the form of lambda, but it cancels within the scale of lambda, because you see it's lambda over lambda. So whatever cosmological constant is there, it cancels itself. But it's relevant for the evolution.
What is your omega matter?
Omega matter is the standard one. Yeah. So the condition is, again, omega matter plus omega lambda should be equal 1. And matter you can consider dark plus baryonic. You can have also the curvature term omega k, the same like LambdaCDM. The difference is just how you modify the cosmological equations.
But you need a dark matter there, right? You need a dark matter there.
Well, we are not sure. I mean, as I said,
because for baryonic acoustic oscillation, you have harmonics, which are position and distance between two, whole harmonical pitch.
Yeah.
They're related to the amount of that baryonic matter and dark matter very, very accurately.
But that's where one would require actually using these backgrounds, okay, to do the calculations and see how well, what is the omega m when you look at the baryonic acoustic accelerations, what is omega m when you look at CMB, what is omega m when you look at supernovas, and see, do you get the same omega m, or you get different omega m's and you have to break omega m to dark matter and baryonic matter.
Yeah, so I guarantee that for an omega m of 0.8 or 0.5, the peaks of the variant acoustic oscillation will be way higher than what we measure. Or there's
For harmonic, it's actually very, very fine interplay with for harmonics.
The real comparison in the center. Yes,
Mm-hmm.
The real comparison should be with omega matter 0.3, right?
Yeah.
So that is what
Yeah.
you're comparing.
But the thing is, my concern with the dark matter is that we could be going after another Vulcan, or maybe we could be drawing epicycles when they may not be there.
No, but I want to understand. So in the dashed line that seems to agree with the cosmological history with the LambdaCDM, you put omega matter 0.275 apparently.
Yes, this is to get a curve that is as close to the LambdaCDM 0.3.
And you want to be there probably.
Well, that's, you want to see how well you can reproduce the LambdaCDM. Because this is just, you can think these are two different approaches. There is a little deviations. Now the question is now, obviously because of these deviations, if you start improving, looking at your data fits, then you should be able to start seeing the difference.
My question is, what if you didn't put dark energy? You replace dark energy.
This is matter. I mean, we don't know, at this point, we don't know it's dark energy, dark matter or not. The dark energy is just the complement of the total matter. And K is equal 0.
Dark energy, but they didn't define what the omega matter is.
Yeah.
Okay, very good.
Okay. So now to this kind of the growth of the density perturbations. The thing is that apart that we see the rotational curves in the galaxy, the way clusters behave, we say, well, it seems that there is something there dark that makes them rotating like this. The growth of the density perturbation is considered to be the strongest argument for dark matter. Basically, if you follow the Einstein de Sitter model without dark matter, and you look at how the density perturbation would grow, they would not grow fast enough to reach the current state that we observe now. And the explanation is, well, we have dark matter. Dark matter creates gravitational potential where the matter settles in, and basically the dark matter kind of seeds the perturbations and their growth. So that's, as I said, we are just poking different places with Professor Mader, and that was one of the things that we wanted to investigate. So with him, we worked hard to make sure that we derived the equations according to the core tensor calculus. And this is the continuity equation, and you see if kappa is 0, then this is the normal continuity equation. But if it's not 0, and now from now on this kappa is minus lambda dot over lambda, this is just the kappa, the time component of this vector that should survive if we want homogeneous anisotropic vacuum. So there's this extra term. Then in the Euler equation, there's another extra term depending on kappa and the velocity there. Now, surprisingly, the Poisson equation doesn't change. The reason it doesn't change is because of the scaling of the energy density. So using these three equations, then we can write equations related to the rate of change of the growth of the density perturbations. Now, the important one that we have to make actually here assumption, something that will allow us to do the calculations with these three equations, was basically, we don't know exactly what are the density perturbations, but most likely we can think that they are different linear, quadratic, cubic powers of their spatial parts. And basically, the actual term that stands here on this right-hand side is this one. But this equation, which is kind of, in a sense, probing, is that a homogeneous function or not? And if it's a homogeneous function, then it should satisfy Euler's equation like this. So n here is basically what is the order of homogeneous function, what type of function it is. And we'll study a few different variations. It seems that n equal 2 makes sense just because it's quadratic, that's spherical symmetric. Yeah. Mm-hmm.
So before going to the math, so the continuity equation with the right-hand side non-zero, it seems that energy is not being conserved.
Yes.
So there's a flow of energy density somewhere. So where is it going to?
Well, the thing is that you have to look at, this is the cotensor calculus. I mean, you have to go through the math.
But there's some physics there, right? So what's the physics?
I agree. I mean, that's actually the other thing that I'm trying to study. There are other models where consider 5-dimensional space-time. And from 5-dimensional space-time, they look actually in terms that are non-conserving. They say matter creation, dark matter creation. The thing is that these equations are just coming when you start doing the algebra on the continuity equation, when you're starting transforming it into cotensor framework, given what are the order of transformation of these variables, so that to write equation that is consistent according to the cotensors. Because the cotensors, they have to have on both sides the same behavior. And that's why, I mean, this one doesn't have it, because basically the Laplacian here behaves the same way like the density, energy density. Yeah. So here, that's why this is n is, and the assumption is just basically this term would be substituted with n kappa delta.
I thought that maybe I'm wrong, but so the first part, if you have a volume, right, that shows the conservation of matter. The second part is associated with the variation of the volume.
Oh, you mean this one?
Yeah, kappa.
Yeah, you can think like this, because the universe is expanding, and obviously the volume is not conserving.
But even in an expanding universe, this is 0. The right-hand side is 0. So this is not variation of the volume, I don't think.
But it's the only interpretation, right?
I don't know
Yeah.
the interpretation.
Well, then you'll see another equation that you'll find difficult and kind of start scratching your head. I mean, also when I coming to him and I was communicating with him, but there's non-conservation here in yeah, it's there, but look at the algebra, and when you go through the algebra, you see that that's the term that should come up.
Isn't that like just your matter is decaying to vacuum?
No, I'm not considering, I mean, all I'm doing is just following the rules of the cotensor calculus. And then doing, well, that's what I should be doing in this new framework, how the equation should look like. And all the change is going from G to lambda times G, allowing the existence of gauge transformation.
There are like models of vacuum which decays, and then you have an observation of this, maybe it can be mapped.
Well, I mean, hopefully. One thing, like earlier today, who was the first speaker? Jay, I don't see it. Oh. Yeah, so basically, you notice that I asked him about the 1 over L, because here we have 1 over T, and actually it's 1 over C times T, which is like 1 over L. I mean, I don't know, it could be some kind of more fundamental theory behind, but at this stage, we are just staying on the usual kind of 4-dimensional theory, but the cotensor calculus is the key there. So if I manipulate these equations, I come to a new expression for second order for the, 5 minutes now. So then I have to do the second part later.
Yeah, during the discussion.
So again, there's 2 terms depending on kappa. If kappa is 0, they're gone, and this is the usual equation. But if they are non-zero, they are non-linear terms, and then you have to solve for them. And we did numerical calculations. He did himself, I did myself, and then we look at, and we saw that the results are the same. And we did it independently. I mean, in my experience was working with him that if something seems wrong, most likely I made a mistake. He was doing this for quite a long time. So here are the results. N is the order of homogeneity of delta. This is the Einstein-de Sitter model. Basically, this is the values for omega m, initial value for the perturbation, and when is the recombination time. Now, then here you have 1, 2, 3, and 4n. We look at also n equal 2 at 2 different recombination times. The surprising thing is that it seems that it behaves the same way. The slope is pretty much the same, the rate of growth. Obviously, the growth is fast enough to actually generate the inhomogeneity nowadays. I mean, it's not like the Einstein de Sitter is here. Here, it's much faster. So pretty much you can accommodate them. But the surprising result was this one. What is surprising here is if you look at matter, basically here is less matter, here is more matter. I mean, this should be actually the blue. I don't know why it looks like dark green. So it's 0. So like 2% matter, 10% matter, 30%, and 0.5. And it seems that the less matter you have, the faster your inhomogeneity grows. And this is the effect of the non-homogeneity, of the nonlinear terms in the equation. So to explain this in another way, I will just show you this one so that I can hook you for the discussion. So basically, this is how the equation of the geodesic looks in the core vector calculus. There's again also a way to derive it from action principle. And if you do the weak field approximation, then you get the equation like this. Now again, this is head-scratching equation as well, especially this term. I mean, you say, well, so if I see something moving and somebody is co-moving with this thing, they'll see it with 0 velocity. So it's really weird. But how weird is actually the whole Hubble expansion itself? But now this helps you understand why the perturbations are enhanced in their growth. Because if you have an infalling flow, this will be enhanced. Something that is moving towards the gravitational center, it will move faster. If you have something outgoing flow, actually it will be enhanced. It would move faster outgoing. And kappa is 1 over t. Early time, actually this is very small. Now it could be 0 practically because of the big value of the age of the universe. But the early times, this would be a very strong enhancing factor that would induce. And the rest of the talk would be actually talking about comparing these two and how this actually results in things relevant to the dwarf spheroids. So I'll stop at this point.
Thank you.
Yeah. So one question there?
Yeah, so I was just,
Just a second.
just trying to,
Yeah.
Hello. Okay. So do you have an explicit time translation breaking in here? So looking at your kappa function, I'm trying to just trace, how everything fit together. So do you have some background functions that are explicitly breaking time translation invariants?
So
I mean, this is in part related to part of some of the discussion that I think has been going on here that maybe is behind.
So the thing is that when you look at the first solution that I showed you, basically you find that it's easier to solve the solutions in some kind of arbitrary choice of time for the equations. But then you find that there is a moment when the scale factor is 0, and this we'll call the moment t initial. I mean, your questions were written originally, you solved them, and this is your t initial. Then you find a moment when the scale factor would be 1 comparing to what nowadays we're considering, and you call this is t final. Then you look at what is actually the overall choice of units that you're using to actually match this with the age of the universe. So the thing is that the equations, everything is covariant, but the moment you start trying to express it in terms of what you're observing now, you actually start breaking all these covariance. And you're forced to...
But you can break time translation invariance in a covariant way. You know, you pick a vector, yes, and you can, you know, you can break it in a covariant way. So I guess, again, the question is there an explicit breaking of...
Well, in a sense, there is, because you see, this is saying 1 over t, right? Yeah. And if I go back here, my equations when I started, eventually this lambda becomes 1 over t. So if you have 1 over t in your Lagrangian, it's breaking automatically your time translation.
Right.
But the
so
thing
you
is
have
that
some god that's twisting a handle
well,
somewhere.
that's what I was trying to explain. Where is the god? You look at your solution and you put the meaning. Okay, when a is equal 0, when a is equal 1, what is the scale? And now the god says, wow, that's your value. It's coming from the physical conditions of how you're matching to.
There's somehow somebody's doing something, and there's not going to be.
Well, the solutions actually is 1 over t minus t0.
So you sort of locally probably violated unitarity in this construction.
No, the solution you can consider it 1 over t minus t0. Then there is no violation in time translation because t minus t0 and everything else is time derivatives. But the moment you want to set t0 to be the moment where a is equal 0, then you're breaking the time translation. Okay? Yeah.
Sorry, but the evolution of delta is enhanced by the EDS, right? Let's see.
This one?
No, the next graph, I think, the next plot.
Okay.
Yeah.
This one?
The previous one, maybe? Yeah, this one. But so if you have LambdaCDM, what you would expect is that at some point when dark energy dominates, the growth is less important. You don't grow as fast as EDS. But here you have the opposite.
Well, we didn't show this, actually. The funny thing was I did some numerical checks. I start with arbitrary n, but then I come up, because this I'm enforcing n to stay fixed. What I did, I start with arbitrary n, see how the density perturbation grow, and then redefine n according to what I get as new perturbations. So the funny thing I observed that there is something like this numerically. And it seems that even if I start with -1, it will grow to around 1.3 or 1.2, and then it will start settling to kind of a preferred value for n. It's kind of and exhibit some kind of similar behavior. But our point here was to show that you don't need dark matter to reach the currently observed inhomogeneity.
Yeah, but anyway, I don't understand. You should have this, you're not showing LambdaCDM evolution, but let's say you want to map to have this, your curve shouldn't grow as that much. It shouldn't be monotonically going up. You should have some trying to reach some
plateau. But what I'm saying is that in these expressions, I'm forcing this n to be fixed for my calculation so I can do the calculation. By hand, I'm forcing it stay on n equal this number. Even if you naturally you evolve to something else, I'm bringing it back. And this kind of breaks this. If I let actually, with my numerical calculations that I did, okay, if I want to redefine what is my n at the next step of calculation, then I see this kind of thing happening. And also some natural n is emerging. But the thing is that it's hardly nonlinear, and the problem is that you want somebody else to cross-check your results to make sure that independently you get the same results.
Just coming back to the same plot, if you go to the extreme and put matter to 0, just the plot we discussed, yes, this
one, yeah.
Yeah, in the limit of 0 matter, there will be, according to your model, there will be only dark energy there.
Yeah, that would be the
density of which fluctuations we are talking about. There is no matter, right?
Well, the fluctuations usually considered to be actually the vacuum fluctuations.
So you're saying that the bigger dark energy, well, the bigger component of dark energy, the larger vacuum fluctuation. That's kind of follows from both.
So since we know that there will be some vacuum fluctuations, right, in the early universe, basically these vacuum fluctuations would start growing. Some of them would collapse, some would blow out, and then you start following this kind of behavior. I mean, the thing is, would pretty much depend on what model for delta you would like to kind of consider its relevance. So for empty space, I mean, I'm not removing the vacuum fluctuations, they are still there.
I mean, but how are you going to form structures? How are you going to form galaxies if you have just vacuum?
I mean, the vacuum somehow.
No, I was because you need the well, seeds for large structures formation.
I mean, that's a good point.
I mean, you need some mass which form the seeds, right, for the large structures formation. Because.
So I'm not sure what would be undefined in the moment when you say omega 0.
So the seeds are understandable. If you have some vacuum fluctuation or inflation would like use these seeds. But after that has to evolve. And to evolve in forming structures, you need matter. I mean, just
well, how did the matter appear? Do we know?
Through some influence on decay.
Well, that's the vacuum decay. I mean, we don't know what is the field lambda.
I still need matter, no?
I mean, the thing is that we don't know how matter came up, right? So this is the egg and things. I mean, but your point is actually very good because I don't think we tried to see what will happen in the ultimate omega matter equals 0. Because this would mean something we have to go back in these equations and see how things would change. Most likely it will be related to here. Omega m equals 0, then you have a specific form for the rate of change. Oh, actually that's another point. If you say if you have mod omega matter equals 0, then your vacuum grow like t to the second power. Now, all of you remember the Robertson-Walker. There's a scale factor A that's allowed to go to 0. But if you think about it, we are shooting our feet. We are putting actually singularity on our metric to start with. What is happening with this actually in this model, and we noted in the paper, is that if you look at how the scale factor grows, the scale factor actually grows like t to the squared, but then lambda was 1 over t. And what goes inside is lambda squared, which is 1 over t squared. So this takes care of the singularity A equals 0, the moment of the Big Bang, and actually washes out and say, well, there's no singularity at the Big Bang. These are the two rods that are too far from us, and we see them as a point. But if you go closer, then you see that there's no singularity.
Okay, I get that point. But if you change age, you're going to change the age of the universe. Because if you change how age evolves in time, you're going to change the age of the universe. That's quite well measured. So how can you change the age of the universe? So you solve one problem and create...
No, there's no solving one problem here. You see, this is consistent. The thing is that lambda omega m here doesn't have to be exactly the omega m for LambdaCDM. But there's a omega m for the scalar variant theory that would be close enough to reproduce the same behavior like in LambdaCDM. Yeah.
So I see the discussion has already started, right? Okay, let's thanks.
Yeah. Thank you.
So Jay will take over now, and well, we have already have Yvonne is going to give a second half effort.
Okay. So we'll start with that then, or
It's up to you. You're the boss.
yeah. All right.